This problem is similar to the vertical charge distribution where we had to find the voltage of a point P right above the top tip of that vertical line charge. In this case, it's horizontal, and we are trying to find the voltage of a point P outside of the axis of that line charge. So it's going to be a little bit complicated because we're adding this new dimension into the problem. However, the equation for voltage is going to be the same. We are going to start off with capital V equals to, now instead of 1 over 4 pi epsilon naught, I'm just going to go ahead and write it as K. So we can say that K is 1 divided by 4 pi epsilon naught, just so we have a little shorthand. So V is equal to K integral 1 over R dq. Now, like I was saying earlier, you rarely do an integral with a dq. What you do is you try to get dq in terms of d space, some sort of spatial element. So what we're going to do is we're going to take the fact that charge density lambda is equal to dq over some sort of infinitesimal space here. We'll call that dx. So dx being some sort of variable infinitesimal piece of space on that line. And we're going to take that from A to B. Okay, and that's going to signify what the charge density is, which should be uniform in this problem. dq is then going to be lambda dx, again, from A to B. So if we were to integrate dq and the integrand here from A to B over all those x values, we should get the total charge of this line here. Let's go ahead and plug this into the original voltage equation. Voltage is equal to K integral from A to B, 1 over R. And instead of dq, it's lambda dx. Okay, that helps a little bit because now we have it as a spatial element, d space. The problem now is that we want to try to link the two values together. So we want to get dx in terms of dr, or we want to get r in terms of x. I find it best to try to get r in terms of x, and it becomes a lot easier. So let's consider what r is first. R is a point or a distance from point P to a particular charge dq on this line. So what we want to do is we want to integrate over all of these r's for the entire line charge here. In terms of quantities we already know, we can go ahead and say r is a Pythagorean's theorem, so we can use r as a hypotenuse. Using Pythagorean's theorem, we say that r is the square root of y squared plus some sort of length here squared. And the length here is just going to be b minus x. So b is this length here. X is just going to be some sort of variable length from the origin to wherever we're looking at connected to P. It's going to be, say, right here for this particular case. So the difference between here and here is just going to be the length of this element. So the second leg of this right triangle that makes the hypotenuse r is going to be b minus x squared. Let's go ahead and plug it in. V is equal to K from A to B, 1 over y squared plus b minus x squared. And let me go ahead and bring lambda out to the front. Since it's a constant, it doesn't need to be in the integral. And we'll put dx at the end. Cool, this is starting to look familiar. If you look up online how to take the integral of, say, for example, taking the integral of 1 over square root of x squared plus y squared, where y is a constant. Then say you take it over dx. There's something on the internet which you can find that gives you the answer pretty easily. Now, the problem is getting this to look like something like that. The problem here is that we have the variable x nestled in with b, and it's also squared. Here we just have d of x. There's no b minus x. So we're just going to do a variable substitution so that we can get dx. Instead of dx, it says db minus x. So to do that, let's consider db minus x, and let's solve for what this equals to. See what this is. This is db minus dx. Now, since b is a constant, the infinitesimal difference in that constant is just going to be 0, right? So the db ends up being 0. And what we have left is a negative dx. So therefore, dx is a negative, is equal to a negative db minus x. So let's substitute dx into the integral. V is then equal to k lambda integral a to b 1 over y squared plus, I apologize, this is inside a square root. So 1 over square root y squared b minus x squared. And dx is just going to be a negative db minus x. We'll put the negative out in front. So now we have d of some variable, and we have this as that variable. So now it mimics this sort of form, and we can look up online to find out that this form ends up being log of square root y squared plus x squared plus x, and then plus some sort of constant c. At the end of the video, I'm going to show how to actually derive from this integral to this answer. But for now, what we're going to do is accept it the way it is. So this ends up being negative k lambda. And you have to do this carefully. It's going to be a log of b minus x. So that's the x here. Now it's b minus x for this particular situation, plus square root of y squared plus b minus x quantity squared. And x goes from a to b. You could already see there was a potential mistake over here, because once we did a variable change, I needed to change the parameters, or sorry, the limits of integration. However, I specified that x will go from a to b. So therefore, in this solution, only x will go from a to b, not b minus x, just x, okay? So let's go ahead and do that. We're going to separate this a little bit. So this will become k lambda log b minus b plus square root y squared plus b minus b squared minus negative k lambda log b minus a plus square root y squared plus b minus a quantity squared. All right, the rules of integration say that if you have a log with an argument minus a log with another argument, that is the same as the log of the first argument divided by the second argument. So this becomes negative k lambda log b minus b plus square root y squared plus b minus b squared divided by b minus a plus square root y squared plus b minus a squared. Second thing we can do is we can take this negative and basically put it over to this log, so it's a negative log. And a negative log basically switches the argument around. And to make it easier, you could just say, well, if you multiply both of these by a -1, or I guess you get rid of the negatives here, that means you'll have to switch around the argument. So instead of log of b minus b so forth minus b minus a so forth, it's now log of b minus a so forth minus log of b minus b. So the negative would switch around the which argument came first or which term came first. So that's the same as saying that if you were to get rid of the negative, you switch the numerator in the denominator. So let's make it simple by just saying this is equal to k lambda without the negative log of a minus or b minus a plus square root y squared plus b minus a squared, all divided by the numerator b minus b plus square root y squared plus b minus b quantity squared. Now let's simplify. B minus b is 0. B minus b is 0 in here as well. This y squared is square rooted to become y in the denominator. So finally, the answer becomes k lambda log b minus a plus square root y squared plus b minus a squared divided by y. And that is your answer. I'm going to go ahead and box it since it's a little messy everywhere else. Cool thing about this, we got it in terms of everything we needed to get it in terms of. So we have k, which we should already know is 1 over 4 pi epsilon naught. We have in terms of lambda, b, a, and y. So this is the final answer. This is the voltage or the potential, I guess a better way of saying is the potential at point P due to this line of charge. Now go ahead and stop the video once you're satisfied with this. And in about 3 seconds, I'm going to show you how to actually do the integral from here to here. Let's go ahead and do this integral in kind of in the context of our problem that we had just recently, where y is a constant and x is the variable in which we're integrating over. And we'll make it an indefinite integral, so there'll be a plus c at the end. First, let's let x equal to y tan theta, and therefore dx will equal to y secant squared theta d theta. The derivative of tan theta is secant squared theta. Plugging x and dx into the equation, we get y secant squared theta d theta divided by square root y squared plus y squared tan squared theta. We're going to go ahead and invoke a trigonometric identity where secant squared theta plus minus tan squared theta is equal to 1. So therefore, secant squared theta is equal to 1 plus tan squared theta. Okay, so if I were to take y squared out of the denominator inside the square root sign here, I would have y squared times 1 plus tan squared theta. So this will now then become y squared times secant squared theta. So the integral now is y secant squared theta d theta divided by the square root of y squared 1 plus tan squared theta, which is then secant squared theta. This ends up becoming y secant squared theta d theta divided by, now we take this out of the square root sign, it's just going to be y secant theta. We're going to cancel out the y's since they're both on the numerator and denominator, and they're constant. We're going to cancel out one of the secants in the denominator with the square of the numerator. So this ends up becoming secant theta d theta. Again, this is just a identity for integrals. You can find easily that the integral of secant theta d theta is log secant theta plus tan theta plus, we'll call this c prime. We call this c prime because eventually we're going to turn it into a c upon further analysis. So let's go ahead and get this into more familiar terms. Secant theta, again using this trigonometric identity, is going to be the square root of 1 plus tangent squared theta. So let's go ahead and plug that into here. This ends up being log of square root 1 plus tangent squared theta plus tangent theta plus c prime. Okay, now what we're going to do is we're going to do a substitution back into the original values that we have here. So we want to get it now in terms of x's and y's. So first of all, we see that tan theta is just x divided by y. So tan squared theta is x squared over y squared. Again, we'll get tan theta in terms of x over y. Okay. The last step is to try to get a common denominator and try to bring out the y over here using the identities or the law of logarithms. So if we were to extract y and try to get it as a universal denominator, it'll look like this. With the identity or the law of logarithms, if a logarithm with an argument divided by something else, so some value divided by something else, that's the same as saying logarithm of the numerator minus the logarithm of the denominator. So this ends up being logarithm of just the numerator minus the logarithm of y plus c prime. But logarithm of y is just a constant since y is a constant. So we can absorb it into the c prime to simply make it c, where c is equal to negative logarithm y plus c prime. This will end up finally being log y squared plus x squared plus x, all of this plus c. And that is the solution to the original integration. So we plug that in to the problem that we had at hand, and we can solve it from there.